Good morning, everybody. I'm glad you guys made it down here. I realize it was raining this morning. It's kind of hard to, drive in the rain, but I'm glad you guys are here. My name is Belinda Gonzalez. I am from the University of Texas at El Paso. This summer, I was working under the mentorship of Dr. G. Lang Farmer, which I will call Lang from now on. The lab work is done under Emily Verplanck and awesome editing skills by Jessica R. Stanley. They're all from the University of Colorado at Boulder. Okay, so our study focused on producing isotope data in order to better understand the source of magnetism in the Rocky Mountain region. The purpose of our project is to compare and contrast composition of volcanic basaltic rocks in the continental interior with ages ranging from Late Cretaceous to early Tertiary. The reason why we're looking into these rocks is because the mechanisms by which these rocks generated and erupted the lithosphere are not very well understood. In addition, looking at these rocks might bring up evidence of how much the pre-existing continental lithosphere was involved in the generation of these magmas, if at all. We will do this by producing radiogenic isotope data from these volcanic rocks. Oh, where's my pointer? And that will be done by performing chemical separations and then putting that into thermal ionization mass spectrometer. We will look at the major and trace elements, the radiogenic isotopic data, and the mineralogy to better understand these volcanic rocks. So here I have a map. Sorry, I'm kind of having trouble with this, so my ears are a bit small. Okay. Can everybody still hear me? Perfect. Okay, so we have our region here. The first little area we would like to look into is Slide Rock Mountain, and it's a little purple point right here. Those samples are actually closely associated to my project, as those are the ones that Lang picked last year. But we're also going to be integrating a different area, which is the Colorado Mineral Belt here in orange. And those data sets are going to come from NAVDA and from another student that was from the University of Colorado, and her name is Treasure Bailey. She graduated actually around 2007. The questions we are addressing are why do we find said volcanoes 1,000 kilometers inland from the continental margin? What are the chemical signatures of these two volcanic sweeps, and what do they tell us about the source regions from which they crystallized from? So let's zoom out a little bit and talk about the tectonic setting of this area. The laramide orogeny is normally attributed to the flat slab shallow subduction of the Farallon Plate under the North American Plate. And here I have an excerpt from a paper that Jones and Dr. Farmer wrote in 2011, and it just kind of shows the subduction, and then eventually there's going to be a thickened sort of crust right here. There are actually a couple of stages to this orogeny. First, there's the interaction of the lithosphere at the margin. Then there's the shutdown of the volcanic arcs near the subduction zone, and ultimately volcanism and mountain building. So that's layered orogeny. The volcanic sites coming back down, zooming in, we're looking into the Colorado Mineral Belt, which is a belt of plutons and mining districts and volcanic rocks. So it's located around Denver, central Colorado. It's kind of very extensive. So specifically from the Colorado Mineral Belt, we're looking into the Windy Gap member, and that's the oldest layer of the Middle Park Formation unit. It consists of predominantly volcanic clastic rocks with some andesites, trachyandesites, and volcanic flows, and lava flows. Going into our second location, it's going to be Slide Rock Mountain. It is the remains of Late Cretaceous early Cenozoic stratovolcano, predominantly composed of volcanic clastic rocks with some basaltic andesite flows. Okay. So just start comparing and contrasting the areas. First of all, I'd like to start by saying that both areas erupted approximately 70 million years ago, so they're really similar in time. But there's a difference between the lithosphere through which they erupted. The Windy Gap member erupted through Proterozoic lithosphere, which is about 1.7 billion years old, and the Slide Rock Mountain erupted through Archean lithosphere, which is about 2.6 billion years old. And here we see it's on the Wyoming Great On, and just a little bit different. Okay, so my project was actually separated into 4 components. We have the isotope geochemistry component, which I am going to talk about now. Just a quick little diagram of what I was doing. isotopic column separation. So here we have a real-life picture that I took in the lab, and just kind of a little diagram of what it would be. We have a little fret, and basically what we do is we drip our samples and acids through these little columns, and then the fret basically acts like a little filter to, I guess, isolate specific elements. Okay, so a little diagram there. And then eventually we have all of the necessary elements that we would want into the collection cup, and we would put that into the mass spectrometer. So here's just a quick little overview of my methods section. We started by crushing these volcanic rocks, and we had 2 separate samples. We crushed them, powdered them, and then made them into a dissolution where we got rid of the organic material and the iron and stuff like that. Then the next thing that was to follow was actually a series of, as you could see in the bottom row, a series of drying and adding more acids, so through specific columns. And then eventually, what it all boils down to after this process is this tiny 1 millimeter speck right here, which is the acceptable form to put into the mass spectrometer. It was fun. So I'm just going to talk a little bit more about thermal ionization mass spectrometry. We have a picture of Emily, and she actually is loading our slide rock samples and running them through the spectrometer. Thermalization mass spectrometry is a method of obtaining isotope ratio measurements of specific elements. So basically what we do is we purify the sample, and then we run it through the source of the mass spectrometer, and then it gets ionized and then accelerated into a magnetic field. Okay, the second component of my project is NAVDAT, and it's actually split up into 3 separate subcategories, because I did a couple of different things with NAVDAT. So NAVDAT actually stands for the North American Intrusive and Volcanic Rock Database. It is an online compilation of age, chemical, and isotopic data, and it can be found at this domain right here, www.navdat.org. It's free to the public, and anybody can access it. The purpose of using NAVDAT is to create bulk composition plots in order to seek patterns in both sites. So going more into that, this is actually one of the, this is actually a couple charts that I made from NAVDAT. The first row is all Colorado mineral belt. The second row is all slide rock, and each column is separated into specific major oxides. So we're just going to compare and contrast these 2 sections again. As we could see, there's negative trends in iron oxides, calcium oxides, titanium oxides, and then we have both of these volcanic, both of the volcanic activities in this site also have this hook in the aluminum oxides, and we could see where there's an increase, I guess, right here, right around here in both areas is when you would start to form the feldspars. What we can conclude from these charts is that both areas display similar trends when plotting major oxide abundances versus SiO2. Here's actually an example of the data we were using. This is actually specifically Treasure Bailey's data that was integrated into my project for the Colorado mineral belt. And we just kind of manipulated the data from there. Okay. The third component of my project was to create these Harker diagrams that were then fitted with TAS diagrams, which is total alkali silica. And we did this so that we could look at the composition. So as you could see in the Windy Gap member, and this is the data set that includes Treasure Bailey's data. Hers is going to be in green and yellow. Mainly on both sites, we could see that they plot in the basaltic trachyandesites and trachyandesite regions of the TAS diagrams. So they're really similar in that way too. Just another piece of evidence that states why they're so alike. Okay, and the last element to my project, which is mainly the heart of my whole research, is going to be this chart and the chart that is to follow. Let me just go into a little bit of detail, just trying to explain it to you guys. This chart this little line right here is going to be CHUR, and CHUR is a normalized ratio that makes it easy to see what the isotopic variations are. So that's CHUR. In general, a rock that has the same isotopic composition as our standard, we're plot at 0 epsilon neodymium, which is true. Okay. So just a couple of things that we would see if we were to plot something on this type of graph. If we were to have, which is not us, this section right here, if we were to have more samarium relative to neodymium right here as depicted by this arrow, then we would have positive epsilon neodymium values. What we do see, and this is kind of like a little window into the next slide, are these two Colorado mineral belt slide rock. We see negative epsilon neodymium values, so that means that there's a lower 147 samarium to 143 ratio. The way the Earth works is it's light rare earth element enriched. Rocks plot as high epsilon neodymium values, and reservoirs that have had a melt extracted yield positive values. Okay, so this is the graph that's actually the heart of my research. What we could see here is that they're both plotting at negative epsilon neodymium, but as we could tell, the slide rock mountain is a little bit more negative than the Colorado mineral belt. So we can interpret that as being related to the different ages of the lithosphere through which they erupted. So what we could conclude from our graph is that the mantle magma source was actually a continental lithosphere. Apparently, if you extract magmas from a chondrite reservoir at different times, for example, 2.6 and 1.7, then the magmas will have different epsilon neodymium values that are related to their age. The things I would like you to take away from my presentation are the observations that we made that the bulk compositions were similar in previous graphs. The magmas could not have originated from sublithospheric mantle, or else they would have produced high epsilon neodymium values. So not from anywhere else that's not the lithosphere. They could not have been from the crust, or else we would see a lot less mafic sample. And then, therefore, the negative epsilon neodymium values in these mafic magmas suggest that the parental magmas must have come from an older pre-existing continental lithosphere. I would like to thank Aisha and all the awesome UNAVCO staff, Beth, Melissa. They put a lot of hard work into this, Jilang Farmer, and Emily Verplanck for taking their time to, teach me all these things, and all the awesome writing mentors that apparently volunteer, Rolf, Kaylee, Jessica, because it would not have been anything like what I wrote it originally, and the people who wrote my letters of recommendation. Obviously, the people who have helped fund this. It was awesome. Thank you.
All right. Any questions for Belinda? Amy.
Yes.
So in point 4, you kind of allude to like future implications. Sorry, I'm not holding this correctly. You allude to kind of future implications for your research. If you were, given probably like
A bit more time.
a bit more time, what would you do with this data?
So if I were to have, say, a couple of more weeks, I would definitely go more into my isotope data, because I did produce data for lead and strontium and all these other types, and that I was not able to put into models to use as part of this presentation. But I think that if I had more time to make those models, then I could even conclude an even more in-depth conclusion about the lithosphere and the magma.
Any other questions? No. Okay. Thank you, Belinda.